Thank you. First, I want to express my thanks to the organizer to give me the chance to present a talk here. And this is a joint work with Professor Herbert Koch here. The title of my talk is the global well-postedness of the 3D Kadomtsev Petviashvili II equation. So that's my talk's organization. And we are consider the three-dimensional KP2 equation. Here, three-dimensional means that for the x is 1r in R and y is in R2. And you can see here, we are considering KP2. Here is a plus. If it's minus, it goes to the KP1, but it's totally a different story. So we just think about this KP2 equation. And we want to set up the well-posted result in a suitable function space x. So we are thinking about some x. So what's the motivation? Of course, we want the x to share the basic construction of this function. So we have this function has some basic symmetry construction. It is translation invariant in x, y, and t, and also the scaling. If U is a KP2's equation solution, and this scaling also conserves. The third one is very important for our argument is that the Galilean transform it is right like this. Here C is R2, and this also conserved. And we want to write it into the Fourier transform side. It looks like here. And of course, the tau is the Fourier variable of t, of time, and c is corresponding to x, eta corresponding to y. And you should remember that here eta is two-dimensional, and c, of course, also two-dimensional. And the thing is that the c do not change at all. You only translate this kind of eta part. So even we want to study this problem is also because there are we want to get some scaling invariant space. It means that if with the same scaling, in the x space, we want to have this scaling should be conserved. So for instance, we consider the Sobolev space defined by this norm, and S1 corresponding to the derivative over x, and the S2 corresponding to the eta, and the critical for the three-dimensional is this one, S1 plus 2, S2 equals half. And of course, you can have space of type space or any other kind of space functions. And if you remember this Galilean transform, this one always translates the eta away if you translate somewhere. So generally, we are looking for some S2 equals 0. It may control this kind of convert. This is still in this Galilean environment category. So S2 is always we want to think is equal to 0, and of course we want to think about any other equation function spaces. So when we also consider a two-dimensional case, two-dimensional problem also share the whole symmetrics, the translation invariant, the symmetry, the scaling, and the Galilean transform invariant. And there are a lot of works in the category of this as HS2 is S0. Here, this one S means the regularity over x and 0 over eta part or y part. And we start with the Bourgain's 1993's work for the global well-postedness in L2, and later Tukakov in 2000 and Tukhago-Tatsvitkov, and also Isazamiya and Haddad in 2008. And in 2009, people already can, Haddad, Hare, and Koch had already can set up the global well-postedness and Symmetry in the critical case. The story starts that I want to consider this kind of two-dimensional case with the initial stage in some L3. That's my start point to consider this kind of function space. But I struck into such kind of case. If this is linear solution, you will see later. Here's R3. I started to consider a two-dimensional case, but I jumped here. Before I thought I can have this kind of estimate, but I don't know if it is true or not so far. So, but during this period, I have some idea about the decomposition over the eta part, because you want to have some kind of this kind of estimate, the regularity over eta part, or the should be considerably in it. Unlike here, you are always canceled this kind of estimate. So I turn to the three-dimensional KP2. I want to see what happens here, and in the first literature is Tatsvitkov in 1999. He set up the local well-postedness in the HS space in the R3, and the HS function space is defined like this. Here is zeta is a three-dimensional point, and is the HS space. And later, in 2007, Isaza Lopez on the Mia put down the local well-postedness into this SR space, and this one they have some strong derivative over C, and also you cannot ignore the eta part. 2007, Haddad has set up the local well-postedness for almost all subcritical cases. If you remember, the critical case is that S1 plus 2 S2 equals half. Even the R is not corresponding to the eta part, but it still almost gives a main idea. So that's why we compare to their work in the R2 space. So we want to see what happens in this kind of critical space. So if we want to start with this estimate, we want to have some basic idea about the linear solutions. Is that here is L2, a unitary L2 operator is the linear solution to the linear equation, and then we have the Strichartz estimate for this kind of estimate, and also here as this kind of search. The second one is new. You can see because that the eta part is not compactable, so you cannot have the Sobolev space because this part is only derivative. Sorry, this derivative is only on the x part, so the Sobolev embedded cannot allow you to from this already know estimate to this Strichartz estimate, but we will use the frequency decomposition according to the C part. You can always decomposition this into some frequency part, and From the Strichartz estimate, we can have this L4 estimate. It's not hard. Yeah. And for this, for the low frequency with high frequency, this multiplier L2 norm is also have this kind of estimate. It's also not very hard. And we want to work in the U2 V2 space. This kind of U2 V2 space is already very standable up to the work by Hausdorff, Hare, and Koch. So we just want to show you with our Strichartz estimate and with our and with the bilinear estimate, we can have, if this LP LQ satisfies this condition, we have this kind of, you can have this UK norm embedded to the LP LQ, and also the second corresponding to our new Strichartz estimate, and the UP and the VP has some kind of embedding. And the bilinear estimate could have this kind of, the bilinear estimate here can give you this kind of estimate. But if you want to change this one into V2, from U2 to V2, you have to some log lost here. Yes. It's here, Q is less than P. So what we want to do is that to estimate this kind of product. And by Fourier transform, it always can write down into this hyperplanes integral. And the modulation, you have, this morning we have heard a lot, the modulation, or the resonant function, each one has a resonant function, has a modulation, and they plus together, you have this kind of estimate. This function, we can also call it a resonant function, because we are in the KP2. If it's KP1, it's totally different language, but for the KP2, we are always have this kind of lower bounded. This lower bounded is very important for us for the KP2 argument. So after we show us, after we set up all these basic ideas, we can try to understand what happens for this initial data in this kind of estimator. Here F lambda is just in some frequency part for the decomposition according to C, and here is this is a derivative, and we want to have this kind of estimate to see the linear part has the bilinear estimate. If we could do this, and then we can have the Picard iteration and to set up the global well-pointed state, because we are in the critical case, so this kind of bilinear estimate is enough for us. By scaling, we can always scaling this lambda equal to 1, so we want to do this. And here, the x0 lambda is just compared to this one, and this can be, for the linear solution, it can just be bounded by the initial data, so everything should be work if we could do this. Okay, decomposition according to these two UV into according to the C part. We just want to show the difficulties, so we set up. Firstly, if here is, or we compare to this case, there's a low frequency because mu is less than 1 in this kind of estimate. Low frequency has the highest modulation. So then it's easily to put it into L2 because we want to use the high modulation estimate. And this one is, these two put into the L2 norm, and then this L2 norm gives this L4 estimate. U4 and U4, and it goes to U2, V2. So this is okay. And the high modulation gives this term. But if you remember OX, so it's really hard, really far from what we want. The second, if the high modulation goes to one high frequency part, then the same thing happens. We put here into L2 and this 2 into the L2 and use the bilinear estimate I have stated before. And this one comes from this mu minus half comes from the high modulation estimate. And this mu is, and you can get this one. It's almost done. It's almost done. If for this one is okay. Even we can put all the input in waves into the U2 space, but we want to put this W1 into V2. If you want to go to V2, it's not enough. So we have some difficulties here. For the first one, the low frequency is far away to put into this X0 norm. And for the second, we have to replace U2 by V2. It should have some log comes out, so we cannot put it. For the first difficulty, we want to put the low frequency with high modulations into some X0 B space, and B is larger than half. And then you can compare. You can always think about that U2 or V2. It's some kind of, it's not true, but you can think about B equals half. Here we want to use the high modulation, so B is larger. And of course, you have to keep the scaling. It's not just put it into the X0B, but you have to balance the scaling. The second case is that to replace the UP to VP, there comes a log. For this case, we want to decomposition according to eta over C. And because if you introduce this new X0B space, and the linear part will be having some difficulty because it cannot be into this kind of space. So we need to consider it separately. Now we want to see what our initial data is. Firstly, we'll have some observations that C and eta over C share the same scaling. So that means we can start some answers with the Fourier transform supported into this kind of case. That means here's lambda C eta over C equals lambda m. So you can consider they are in this kind of angle. Then by Galilean transform, C does not change at all, but eta will. But this one will go this direction. So this comes for eta. You can consider that C is separate. The step is lambda. The step is lambda length. So it goes the whole directions. So we put all these lengths into some according to the C over eta over c with the size, this kind of size is always lambda. So that's our initial data. Here, I just modify this kind of gamma k lambda into this kind of size because this is L2 norm. This is a two-dimensional case. And case the step in according to the lambda. And we consider all the waves compact into the small square, and then integral into L2 and consider the LP norm outside. This lambda half is you can consider come from scaling or come from the regularity. It's always. So this kind of scaling, this kind of initial data space is scaling invariant and Galilean transform invariant. After set up the initial data, we can have this kind of workspace. First, you can put all this this one into the V2 space, and as we said, that you cannot success if the high modulation localized into the long frequency. So we want to have this kind of XB space to control this the long frequency with high modulation case. Then we could define our workspace. Our workspace is we focus P less than 2, and B equals to B is large, really large, and and as I said, we will be large, very large to almost to 1. And of course, this kind of X space is also scaling and the Galilean environment, because the Galilean environment do not change the modulus, so it doesn't change this norm. So our main result is that for P less is between 1 and 2, and B is B is larger than 5/6, less than 1. Here is B is larger than 5/6, less than 1. Then the initial data problem is global well-post and scattering for a small initial data as we posted there. And the solution is this kind of size. This is a linear part and a non-linear part, and U is in the X space. X depends on B, and of course P. So is the initial data space empty? Now, actually for P less than 4/3 and less than 2, all the Strichartz functions are in this space. But for P less than 4/3, you have to there is some singularity over C equals 0. That means at least you have to put all those solutions, all those initial data with if P less than 4/3, you have to ask for this kind of initial data, have this kind of vanishment. So the main, one of our main ingredients to set up this estimate is that this improves the bilinear estimate. Here, we still consider that there is a low frequency with high frequency. This interact together, but we have some constructor for the low frequency part. Is that for low frequency part, the eta over C is constructed into some size, and this is the size, the big measure. And in the second, and here is just the measure how far these two waves are separate according to these lines. If they are far from each other, then we have batch estimate. If they are very small, but at least they should be, if they are less than lambda, so we don't care about that. If this one larger than lambda, we will have, this one could give us a lot of help. And this kind of estimate give a lot of improvement. The second ingredient is that we introduce this kind of TL estimate, bilinear operator. This kind of bilinear operator is the same like here, but we just decomposition these two waves according to their to how separated in the vertical case, or in this kind of line case, that this size, if they are separated as L size, and we want to think about this. And if this one is less than lambda, because as you know here, if they are less than lambda, it doesn't matter. So we just we don't want to decomposition it further. We stop this kind of decomposition. And this kind of bilinear estimate is also Galilean transform invariant. And by the bilinear estimate and all this, for this bilinear Galilean transform operator, we can have this kind of L2 norm. It's almost this is always we will focus. We will always have this kind of estimate, but it will depend on L, of course, and this can this long frequency, high frequency, and this kind of estimate. To continue have all this bilinear estimates, we can show what we do. So we still start with this kind of estimate. Of course, you can decomposition according to C is the first step. And then we want to put the long frequency part with the 1/2 frequency part together. And we decomposition this TL. And L cannot be less than lambda, because we think that if they are close in the vertical case, it doesn't matter. It at least has the lambda decay. So we have this kind of decomposition. And of course, this TL lambda could ensure you have this. You can always put this one according to into this small size. I mean, because this TL means that their verticals are not far away from that. They are just the distance is L, so you can decomposition it into L. And all this TL can let you with the same L, same center, and the same size, and put them into the wave, small waves. Another observation is that on this hyperspace, because we are always working in this product, so in this by Fourier transform, it's just the convolution, and you will always have this kind of symmetric. For this symmetric, it will give you some more. Firstly, you can change this one as you want. Ijk equals 1, 2, 3, and you can always have some modulation estimate. And more important case is that, sorry, I lost one page. I lost one page, sorry. Remember we are here. U mu v lambda w lambda could be right into L. And for each L, it could be right decomposition further. And by this kind of estimate, we can think about this one corresponding to C1 eta 1, and this one corresponding to C2 eta 2, and this one corresponding to the C3 eta 3. And this means that eta 1 minus from this symmetric, we can change that C1, C3, this eta 2 C2 to eta 3 C3, but they are not exactly the same, but they have this C and eta C3 and over C2. And remember that C2 and C3 are similar, so they are. Now, we know that for all this, they are size L, and each one is less than L. So you will know that in the same size L. So that means that we can continue to decomposition it and so if you remember, now the good news is that we can always have, for every wave, we can have decomposition over C across its dots, and also over the C, eta over C, and they all have some small size. And because the size is already done, so you can further to decomposition into small cases. But at this moment, you will see that our bilinear estimate could work. The improved estimate could work because we at least give one. Generally, we give the long frequency part have restriction over eta over C, and also they are separated in the lines, in the L lines. And you can rotation this TL into other side, this both side. Of course, this one, you want to put this two high frequency into one TL, it should be less. This L should be larger than mu, not larger than lambda. But basically, for our estimate, this kind of estimate is already done enough for us. also. That's what we have right down here. And that's what we have done here. And then for the low frequency, this kind of decomposition didn't change any high frequency or low frequency. It's just the decomposition over the C, eta over C. And these three parts still have one have the highest modulation. And the highest modulation now have the lower bound L square mu. L is larger than lambda, larger than lambda, less than mu. So we can have some trilinear estimate corresponding to what we have difficulty here. We have difficulties here, so we have to reconsider all this kind of decomposition. With all this decomposition, we have this. If one of the high frequencies have the highest modulation, it's not very difficult just to reconsider it, because we have to consider the LP norm, LP prime. And for the low frequencies have high modulation, but its output is also not difficult. For the low frequency with high modulation, but its input wave, now we have better estimate. But here we still need to put this kind of long frequency has high modulation into the XB norm. It cannot be the U2V2 norm, because all our decomposition cannot change too much according to this kind of decomposition. Cannot change too much the bilinear estimate or the high modulation. It's just to restrict it just restrict the eta of C, and we can get a little bit of better bilinear estimate, and we can cancel the log lost for the U2 change to V2 space. And we want to see, because this kind of estimate cannot this space do not contain the linear solution, so we need to put the linear solution into this kind of estimate for the U1 space. The linear part is U1. This one is just the nonlinear part, but for if one is the linear part, because you want to iteration, then the linear part sometimes it should go into the iteration part, and we want to put them into U1 space, and this one works for that. After we set up all this trilinear estimate, then we can finish our estimate. I don't want to show too much. This one is just the start. Have this decomposition, and have this bilinear estimate. And the very important case is that to have this kind of estimate, then the following is just Hausdorff inequality something. To complete the picture, we also consider the P less than 2, larger than 2. And we construct a counterexample that shows that we cannot have, for the P less than 2, we cannot have any solution map that can be C2. So in this case, we see that P less than 2 is not ionist. It's not well-posed. It's ionist. Ill-posed. So our decomposition is also according to our example also according to our decomposition. It means that for this phi has a long frequency and a very high frequency, and for the eta part, it's just for the eta part, they are the same. It means that all these two parts are all in we write is the phi 1 and phi 2. They are all has the same norm for our initial data, and mu less than 1, lambda is larger than 1, and they have this kind of relation. It's just because the resonant function have this kind of estimate. So this what we want to show, and we show that this estimate cannot be true for p less than 2. And the signature is that the picture is that if phi 1 is phi 2 is here, lambda phi 2 is here. It's very small. They last. Sorry. Yeah. It's mu. The size is also mu. Even the size is lambda, but the interval is also mu. Then, if when the phi 2 is decomposition here, and phi 1 is here, and when they put together, the wave should be come down here somewhere. But basically, the size is the same. The eta part is the same. The c part is also the size is same, but the frequency is high frequency. And for this case, you cannot have this estimate. So finally, we gave some remark that for p equals 2, it's our start point, but we lost. And of course, the same argument should work in the two-dimensional case, but if you lost the p equals 2, it make not too much sense for this moment. Yeah, but it should be give some ideas.